Hello everyone, this is Dr. Webb. So we've been through 7 videos so far in a calculus course, and we have not done any calculus yet. But now the times have changed. Now we actually get to start doing some calculus. So we're going to be working on the calculus of vector functions right now. So anytime you want to start doing calculus, the first thing you have to go over are limits. So the nice thing for us about vector functions is, we use vector functions to draw out curves, right? If you have some vector function r of t, then this is kind of going through and describing some path through space. I mean, deep down, this is still, a curve. And all of the calculus, the limits and such that you did in Calc 1 were really limits on curves. And so these are fundamentally the same thing. And so the limits are going to be the same thing. Just some of the notation's going to be different. Right? So if we're thinking about, we have some vector function, let's do this in R3 right now. Then what does it mean to take the limit as t goes to t0? Well, so we have some vector function. Let's say t0 is right here. Who knows what happens exactly at there, right? But then the question is, what happens as you get close to it, right? And so the limit of r of t as t goes to t0, well, you're just going to look at, since a vector function is just looking at each component separately, doing the limit is just doing the limit separately. And so you have this x of t limit. This is looking at things in the x direction. Y of t limit is looking at things in the y direction. And z of t limit is looking at things in the z direction. So you just do them separately. Whatever each of them is, that gives you the limit at that point. And so then the definition of continuous then is exactly the same as before. So it's going to be continuous at t naught if the limit as you approach t naught is equal to the value of the function, is equal to the vector you get when you plug in t naught. And so that's not surprising at all. Okay, so now that we have limits and continuity, now we can talk about derivatives, right? And so the basic definition of derivative is going to be exactly the same, except now this is happening in components, but up here we just have vector subtraction going on, right? So if this is in R3, this is really talking about x t plus delta t minus x of t minus x of t y sub t plus delta t minus y of t z t plus delta t minus z of t. And so that's just vector subtraction, and so that's being done component-wise. And then the delta t that we're dividing by, well, really this is just scalar multiplication by 1 over delta t. And scalar multiplication goes component-wise too. And so we get divide by delta t in each of those. And then we're taking the limit of everything, but then we just saw that you take limits component by component. And so when you then plug in the limit to each of these components, you see that you just have the definition for the derivative of each of the component. So the derivative of r prime of t, it's just going to be the derivatives of x prime of t, y prime of t, and z prime of t, right? And then once we can do one derivative, then we can immediately go and do as many derivatives as we want. So then what's our double prime of t going to be? Well, it's just going to be all the second derivatives. Okay, so what does, if we have some r of t, what is r prime of t and what is r double prime of t? So let's take some r of t. Okay, and so using, let's say, that's our t naught. If we move over some little t naught plus delta t, right? Well, what's the limit doing? Well, it's taking the difference between these two, right? And so deep down, r of t really is pointing to each of these from the origin. So let's say the origin is 0, 0, pointing to each of these. Okay, and so if I want to do the difference between these two, I take the endpoint t naught and go to t plus 1. And so that right there is going to be r of t plus delta t minus r of t. And then the scaling, dividing by delta t, that's just going to scale that, but it's going to keep in this direction. And so whatever delta t is, it's just going to be some vector going through those 2 points. Right? And as you get it closer and closer, you can see what is r prime of t eventually going to be. Well, it's going to be a vector going along the tangent line. So r prime of t is going to be a vector tangent to the curve at t naught. And so then we can go through, come up with r of t's sort of tangent vectors in all of these places. The direction of the derivative of r prime of t is going to be in the direction that we're going as t increases. And so then r prime of t is going to be looking at, well, what's the differences between these two vectors, right? So if I'm kind of thinking about what the second derivative is going to be here, well, I can see the first derivative at this point, it's pointing pretty horizontal, but then when I move further down, now it's pointing down, right? So which way is that vector moving? So if it's going from here down to there, that second derivative, let's choose a different color. I haven't used red yet. Second derivative is going to be moving something in this direction. And that's just sort of looking at the difference between this vector and what's happening onto it later on. And so it turns out, let's clear some of this out. It turns out that the second derivative, if a vector is turning, the second derivative is going to be going in the direction of the turn somewhat. It depends on how fast things are going as it turns, but r prime of t is going to be tangent. Then my acceleration is going to be going somewhere down here, depending upon what's happening with the speed. Right? R prime is going to be, R double prime is going to be one of these, depending on the speed. And we will talk more about this in a little bit. Okay, so if r of t is our vector function representing, if we're thinking about this as representing some point or object moving through space, then what is r of t and everything else really representing? Well, r of t itself is the position vector. And so if we think about the curve, really remember r of t is a vector. And so from the origin, what the vector is doing is it's pointing out from the origin where the object is at different times. So this truly is what r of, say, t0 is, r of t1, r of t2. Okay, and as it moves all the way along, r of t is vectors that are going from the origin towards where the object is on the curve. Okay, so it's pointing from the origin to the curve. R prime of t is the velocity vector. So velocity, this means it's saying what direction and how fast the object is moving. So if you're driving in a car, this velocity vector is combining both what the compass says and what your speedometer says. So the compass is saying what direction, and the speedometer is saying how fast you're going. Okay, and if we just take out the direction and just look at what the magnitude of velocity is, then that's what is speed. So if you just look at how long the velocity vector is, that is telling you how fast you are going. So the magnitude of velocity is the speed. And that's going to become important later, especially when we start talking about arc length. Okay. So then what's the second derivative telling you? Well, that's giving you the acceleration vector. And so since this is a vector, it's actually saying two things. Since this is happening in 2D or 3D, it's talking about both change in speed and change in direction. And so r double prime is really the vector that's telling you about how you're turning. Okay. And so later on we will get into very specifically how, given r prime of t and r double prime of t, how exactly you can see how speed is changing and how the direction is changing. Okay, so let's do an example building up these components, building up this from the bottom up. So this is a very classic kind of physics type of example. So we have a projectile launched at time 0 from the origin. So at 0, 0, let's assume this is in R2. And it's shooting up initially at an angle of pi over 6 above the positive x-axis. So we're starting at the origin. Over the x-axis, it's going up pi over 6. And its velocity, and so this is talking about its magnitude of this, its speed at the beginning is 30 meters per second. And as it flies through the air, let's say its projectile's a box, the only force acting on it, so the only thing affecting its acceleration, is gravity. And gravity is pulling down at a magnitude of 9.8 meters per second. So we can write that as a vector. It has no x component, and its y component is going to be minus 9.8. Okay, so we know that our acceleration vector, which is the second derivative, is always going to be 0 comma minus 9.8. Okay. Now we know what the velocity vector is at time 0. That's what's given to us by the pi over 6 and the 30 meters per second. Right? So we know at 0, let's put 0 in there. The magnitude is 30, and its angle is pi over 6. And so this is saying that, this should be for the first derivative, r prime at 0, well, its magnitude is 30, and angle pi over 6 means it's going to be cosine pi over 6 sine pi over 6. And so this is saying, plugging this in, cosine of pi over 6 is square root of 3 over 2, times that by 30. You're going to get 15 times the square root of 3. And sine of pi over 6 is a half. And so a half times 30 is going to give me 15. So that's the vector magnitude 30. It's going up pi over 6 from the x-axis. Okay, so this is what's happening at r0. But we also know that its derivative needs to be r double prime of t. That's r prime of 0 is square root of 15 over 3 and 15. And so, well, I know that I want the derivative of r of t of the x component to be 0. And so if its derivative is 0, that means that the x component is going to be a constant. So let's give myself some space here. Let's rewrite this over here. My r double prime. Okay, so r prime at 0 is going to be 15 square root of 3 and 15. So we can take rid of that now. Okay, so we know what the second derivative is going to look like. We know what the components are, and we know that these components are just the derivatives of the components of r prime of t, right? So if we know what the derivatives are, how do we go back to it? Well, really, we're just going to integrate it. And so what r prime of t is going to be is integral of both of these. Well, so the first one we're just integrating 0 dt. Second one we're integrating minus 9.8 dt. And so r prime of t, the integral of 0 is just 0 plus c. And so that's just going to be a constant. Let's say that's a constant for x. Integral of minus 9.8 is going to be minus 9.8t plus some constant for y. Right? So how do we figure out what these constants are? Well, same as doing in Calc 1. I know what I want the value to be at 0. So if I plug 0 in for t here and set these two equal to each other, I have r prime of 0 on the one hand is 15 square root of 3 comma 15. On the other hand, coming from over here, it's cx comma minus 9.8t plus cy. Oh, I'm plugging 0 in for t there, so that's going away. And so this is just cx, cy. Well, so this tells me cx has to be 15 square root of 3. Cy has to be 15. So let's plug those in. Actually, let's plug them in up here. (15 square root of 3) minus 9.8t plus 15. Okay. And so now we have the acceleration and the velocity vector. Oh, come on, erase more. Okay, and then last but not least, we need actual r of t. We need the actual position vector as this is going along, but we can do the same trick again, right? So it has to be, its derivatives have to be 15 square root of 3 and minus 9.8t plus 15. And so we can just integrate up to get r of t. And so integrating 15 square root of 3, it's going to give me 15 times square root of 3t plus some other constant. So we'll call it c2x. And then integrating minus 9.8t, I'm going to get minus 4.9 t squared plus 15t plus some other y constant. How do we figure out what the c2x and c2y are? Well, what's r0? Well, r0 is pointing to its position at time equals 0, and at time equals 0, it's at the origin. So r0 is 0, 0. So plugging in 0 to my r of t, you're going to get that c of 2x has to be 0 and c of 2y have to be 0. So let's take them away. And so there's our position vector. So at time t, the projectile is going to be, its x component is going to be 15 square root of 3 times t, and its y component is going to be minus 4.9 t squared plus 15t. And then you can do all sorts of other fun things like this. Now you can figure out, if the land is flat, when's it going to hit the ground again? Well, it's going to hit the ground when the y component's 0. And then we can say, how far did it go in the x direction? Well, we figure out the time when it hits the ground, plug that time in the x component, we can see how far it went. We can do all sorts of fun things with that. Okay, so let's talk about some differentiation rules. Let's do this, maybe let's do this in R3. The example was in R2, so let's do this in R3. So if we're adding two vector functions together and then taking their derivative, well, addition is done component-wise. And so if we're doing derivative of, let's say, x1t, y1t, z1t, plus x2t, y2t, z2t. Well, how do we do addition? We do it component-wise. y1t plus y2t, z1t plus z2t. So now we have our vector function that we're taking the derivative of. Well, when we take the derivative of it, remember this derivative is just being done component by component. And then how do you take the derivative of the sum? Well, it's the sum of the derivatives. And so this is going to be x1 prime plus x2 prime, y1 prime plus y2 prime, z1 prime plus z2 prime. And then at this point, we could break up the x1s, y1s, z1s from the x2s, y2s, z2s, and we end back up with r prime of t plus s prime of t. So, to make a long story short, same as before, derivative of the sum is the sum of the derivatives. Very similarly, if we're multiplying a vector function by a constant, well, remember that constant gets multiplied to both components. But then when you take the derivative, what happens when you have a constant inside the derivative? Well, you get to just pull that constant out. And so same thing happens here. So constant just gets pulled out, and you end up with r prime of t. Okay, now this one's a little bit more interesting. This is something that we can do with vector functions that's a little bit different than anywhere else. So this is f of t is we're going to call a real valued function. It's not a vector function. It's just some scalar function times r of t. And so here we'd be talking about taking the derivative of, it's going to get multiplied to each component. Okay, so now when we take the derivative component by component, in each component now we have a product. So we're going to have to use the product rule to do it. And so that means in the first component, going by the product rule, it's going to be f prime of t x of t plus f of t x prime of t. I think I'm going to drop the t's in there to save space. F prime y plus f y prime, f prime z plus f z prime. And then here we can break these up between the f primes and the f's. So we'd have f prime x, f prime y, f prime z plus f x prime, f y prime, f z prime. And then since each of these have an f prime in them, and each of these have just an f in them, those scalar functions can be pulled back out. And so we'd end up with f prime of t times the original vector function plus f of t r of t, r prime, that prime's important. And so what did we end up with? Well, it's a little bit long, a little bit more of a circuitous route, but we end up with just the normal product rule. So f prime of t times r of t plus f of t times r prime of t, just like the product rule. As old product rule. Okay. So what if we're doing the dot product between two functions and then taking the derivative of that? Right? So remember dot product, if this is x1, x2, x1, y1, z1, x2, y2, z2, then dot product is going to be x1, x2 plus y1, y2 plus z1, z2. These are all functions. I'm dropping the ft's to save some space. And so now we're taking the derivative. Well, now we have the sum of three products. And so we're going to do the product rule on each of those. I'm doing the derivative now, so I can drop the d of dt. And so we're going to have x1 prime x2 plus x1 x2 prime plus y1 prime y2 plus y1 y2 prime plus z1 prime z2 plus z1 z2 prime. And then we can rearrange these like so. x1 prime x2 plus y1 prime y2 plus z1 prime z2 plus x1 x2 prime plus y1 y2 prime plus z1 z2 prime. And then looking at these both look like dot products individually now, but this first dot product on the left, this is the derivative of r dotted with s. And this one on the right is r dotted with the derivative of s. And they're being added together. So we end up with something that also looks like the product rule. This is one of the reasons why this is called a dot product. It's because it has a product rule when we take derivatives. So the derivative of r dot s is r prime s dotted with s plus r dotted with s prime. What if we're doing the cross product? I am not going to do this out, but hopefully at this point I can convince you that this also follows the product rule. And so all these things that we've been calling products or multiplications, when we take their derivatives, they all have their own product rule with them. Okay, so one brief aside on this. So we're going to talk a little bit about composition with vector functions. So when I mean composition, you can't really plug one vector function into another. But what you can do is you can plug a scalar function, a real valued function, into a vector function. So this is kind of changing t, right? So when we're talking about a composition with vector functions, we're saying start with a vector function r of t, and you have some normal real valued function f of t. What is r of f of t going to look like compared with r of t? Okay, so this is what we mean by composition. Right, so that f of t is getting plugged in for t. Okay, so to get a handle on this, let's do an example. So let's let r of t be t cubed. And then eventually we're going to plug in, for f of t, we're going to plug t squared into that. Okay, so r of t, so this is a vector function r2. What exactly is this going to look like? Well, whatever t is, that's what x is. And then y is going to be t cubed, right? So the relationship here between the x component and the y component is that if I take the x component and cube it, I'd get t cubed, which is equal to y. So this vector function is drawing out the curve x cubed equals y. Okay, and so this is what, when t is equal to 0, we're right there. And as t increases, we're going up this curve. Okay. And so, like in this one, if I start plugging in points, they're all going to lie on this curve. Okay. So now let's look at what r of t squared looks like. So everywhere where I had t before, I'm going to replace it with t squared. So t becomes t squared. And then for t cubed, I'm going to have t squared. And then cubing that, well, a power to a power is going to give me t to the 6th. Okay, and so this is my r of t squared. So let's see what curve this is drawing out. So let's do what we've done before. Start plugging in some values. So at 0, I'm going to get 0, 0. So it also is going to go through the origin. When t is equal to 1, x is going to equal to 1. Y is going to equal to 1. Right? So it is also going to hit the point 1, 1, as on the curve. And I think if I went to 2, that would be 4, 64, which is way off of this graph. So let's try and pick some smaller numbers. Let's pick the square root of 2. So if I let t be the square root of 2, when I square that, I'm going to get 2. And then when I take the 6th power of the square root of 2, well, the 6th power of the square root of 2 is the same thing as 2 cubed. So that's going to give me 8, which still roughly, it's still on this curve, just going up here, right? And so, in fact, any value of t I plug in, I'm still going to land back on this curve. In fact, because the x component is squared, I'm always going to land on the positive side of this curve, to the curve to the right of the origin. Right? And how do I know I'm always going to land on the curve? Well, I still have this property that if I take the x component here and cube it, well, I'd still have t squared cubed is t to the 6th, which is y. So this still has the basic, geometry that all of the y components here are just going to be the x components cubed. And since this curve is the curve of all those points, I'm still going to land on those points. So what has this composition done? What has plugging f of t gone in here? Well, it hasn't changed the points on the curve. It's changed the speed in which we move along it, right? So if you think going from 0, 1, 1 to square root of 2, I'm already way up to here, whereas before I'd have to, in the original function, I'd have to let t equal 2 to get there. Right? If I set t equal to 2, I'd be much further higher out than in the original function. So what this t squared has done is it hasn't changed the curve. So it's the same curve. Let's say we're talking about this. It's the same curve, but we've changed the speed that we've moved along. Okay. And really deep down, what we've done is we've actually given a different parameterization. It's technically what's happened for the same curve. And in fact, any parameterization that you want, you can get from plugging in a composition like this. Okay, so now let's talk about then what the chain rule. So if you plug in a scalar function, a real valued function into r of t, what's that going to look like? Well, so that's going to be taking the derivative of x of f of t, y of f of t, z of f of t. And so now we have a chain rule in each component. And so following the chain rule, this is going to be x prime f of t times f prime of t, y prime f of t times f prime of t, z prime f of t times f prime of t. And then looking at this, everywhere I have an f prime of t in there, so I can pull those out. And we end up with x prime f of t, y prime, f of t, z prime, f of t times f prime of t. And then, taking a look at this, well, the components, really it's x prime with f plugged in, y prime with f plugged in, z prime with f plugged in. And so this is just the derivative of r with f plugged in times f prime of t. So this looks like the chain rule that we know and love. So same as old chain rule. So looking at this, how do we interpret this, say geometrically, knowing that r of f of t is still drawing the same basic curve? Well, on the other hand, we get r prime of t with f of t plugged in. And so this is talking about the tangent vector. This is giving a tangent vector, but then we're multiplying by the derivative of f, right? But it's a scalar, and so this doesn't affect direction. Just magnitude. So at any point, changing these parameterizations it's not really changing the direction of the tangent vector. Unless it's negative, then it would just be flipping it in the opposite way, but it's still lying on the same tangent line as r of t. And so it lies on tangent line to the curve. But the magnitude is different. And remember, what's the magnitude of that derivative? That's talking about speed. And so when I say, what is plugging in, what is composing some other real valued function, some other scalar function into the vector function do, it's not changing the curve, it's changing the speed in which you move along the curve. And this f prime right here, that is telling you how the speed is changing. So f prime of t tells us the factor of the change in speed. Okay, so last but not least, and I'm not going to speak very much about this, what about integration of vector functions? Well, we've already did this a little bit when we did the example starting with the acceleration vector and then going to the velocity vector and then to the position vector. And so what did we do? Well, since the derivative is done component by component, integration is just the mirror image of that. Integration is also done component by component. So for integrating r of t, whether it's a definite integral or indefinite integral, this is just going to be the integral of the 3 or 2 or however many components you want, done separately. So straightforward, how do you integrate a vector function? You just do it component by component. Nothing more exciting to say than that. One of the main reasons I don't want to spend as much time on this is that unless you're going from like a velocity vector to a position vector or an acceleration vector to a velocity vector, there's not a whole lot of geometric meaning to what the integral does. There are in some cases, but usually not. And so you can do it if you need to, especially, and sometimes you need to if you're going from acceleration to velocity to position. But in general, this is not nearly as important as what the derivatives do. And that is all I have for you for this video. I will see you again soon.